Hello and welcome to this video. Today I will be discussing info about matrices that is not in the A-level further maths syllabus that will be useful for exams such as STEP. So first of all, what is a matrix? So as I'm sure most of you know, a matrix looks something like this. For example, this is a 2x2 matrix. Matrices can come in any sizes, so they could be 6x7, 12 by 46, just any size. But for now, we'll just stick with 2x2 matrices. So if we have a two-dimensional plane and draw the y and x axis, and we can label two vectors on here, the I and j vectors. The I vector is this vector here. So the I vector is equal to 1, 0. So it's just going to the right by 1. And the j vector is equal to, so let me just write this as equal to I. And the j vector, which is 0, 1, is just a vector pointing vertically upwards. And with these two vectors, we can reference every point in the two-dimensional plane by using a combination of them. And the reason we can do that is because they are orthogonal. And what this matrix represents is the way in which the I and j vectors change when this transformation is applied. So, for example, in this transformation here, the 2 and the 5, they represent where the I vector goes. So the I vector will end up at 2, 5. And the j vector will be moved to 3, 4. So when we apply this transformation, this is where the new basis vectors, which mean the I and j vectors, end up. And so all other vectors on this plane will follow similar transformations in the I and j direction. The next thing that I quickly want to cover is determinants. So the determinant is a very important property of a matrix, and most of the information about determinants is covered in A-level further math, but there is a tiny amount that I just want to go over. So a determinant of a matrix determines the area of which an area of a shape is multiplied by. So for example, if a shape had an area of 2 and then a matrix transformation was applied to it, and that matrix had a determinant of 5, the area of the new shape would be 2 times 5, which is 10. And this idea of determinants can be extended to 3 dimensions, or I believe even higher dimensions. And so, for example, in 3 dimensions, it would determine the scale factor at which the area is multiplied by. So the only thing I want to cover is what happens when the determinant is 0. So when the determinant is 0, it means that the area of a shape on the two-dimensional plane becomes 0. And the only way for a shape on a two-dimensional plane to become 0 is if all of its points are collinear. And what this looks like is all the points would lie on a certain line that goes through the origin. And the reason it goes through the origin is because the point 0, 0, is always mapped to itself after a linear transformation. And this is because the word linear in linear transformations has two properties. One of them is that the point 0, 0 is always mapped to the point 0, 0. And the second property is that any straight line on a two-dimensional plane, or I believe probably even a three-dimensional plane, after a linear transformation has been applied to it, that line must remain straight. So after transformation, that line can't be bent. No, I'm trying to record, Mama. Shh! Mama, please, I'm trying to stop speaking. Okay, so the next topic that I want to talk about is properties of inverses and transposes. So I'm sure most of you know what the inverse of a matrix is, but a few of you might not know what a transpose is. So the transpose of a matrix is when you swap the rows and columns of a matrix. So for example, the transpose of A which is usually written as AT, will be equal to 1, 3, 4, 2. So you can see how the 3 in the top right corner has gone to the bottom, and the 4 in the bottom left hand corner has gone to the top column. And so the transpose of B, which is written as B to the T, would be equal to 0, 3, negative 4, 0. And this just doesn't work with 2 by 2 matrices. It works with matrices of any shape. So for example, if I scroll down, if I have C equal to the matrix, let's say 1, 2, 3, 4, 5, 6. I know, very original. Well, the transpose of C, so C to the T, would be equal to 1, 2, 4, 3, 6, 5. So as you can see, the transpose of a matrix is quite simple to calculate once you've seen it once. Now I'm just going to go through some of the properties of transpose matrices that can help you simplify expressions that involve transposes and inverses. Okay, so the first property is if we have an expression like this, so A plus B to the, that is A to the A plus B, that is transposed, this will be equal to A transposed plus B transposed. And I think this result is quite intuitive, but I'll just demonstrate it with the following matrices. So A plus BT, so if we substitute A and B in, we'll have 1, 3, 4, 2 plus 0, 3, minus 4, 0. And then we're taking the transpose of this sum. Well, that will be equal to the transpose of 1, 6, 0, 2. And this will be equal to 1, 6, 0, 2. If we instead use the right hand side instead of the left hand side, we will get 1, 3, 4, 2 T plus 0, 3, minus 4, 0 T. And this will be equal to 1, 3, 4, 2 plus 0, 3, minus 4, 0. And this will be equal to 1, 0, 6, 2. which is the same as the transpose of A plus B. And so we can see that this result is true. The next identity is that AB, so the transpose of A times B, is equal to BT AT. And so if again we use the matrix above, we will get that, so 1, 3, 4, 2 multiplied by 0, 3, minus 4, 0 will be equal to minus 12, 1 times 3, so 3, minus 8, 12, and then the transpose of this will be equal to minus 12, 3, minus 8, 12. If we now look at the right hand side, so the transpose of B, so BT, will be equal to 0, 3, minus 4, 0. AT will be equal to 1, 3, 4, 2. And so multiplying the transpose of A by the transpose of multiplying the transpose of B by the transpose of A will give, so 0, minus 4, 3, 0 multiplied by 1, 4, 3, 2, which equals, so 0, minus 4, minus 12, minus 8, 3, 12 as required. And so clearly the identity above holds in this case, and in fact it holds for any matrices A and B. The next identity is in the A-level further math syllabus, and it is the inverse of A multiplied by B is equal to the inverse of B multiplied by the inverse of A. And I'm not going to prove this identity because it would take quite a long time, just trust me if you haven't seen it before. And following on from this, if we have 2A and we want to take the inverse of this, well, this would be equal to half A minus 1. And the last identity that I want to show is that if we have a matrix M and we take the transpose of it and then we take the inverse of all of that, it will be equal to if we took the inverse of M first and then took the transpose of it. And to demonstrate this proof, I'll first need to use the identity matrix, which is I is equal to 1, 0, 0, 1. And we're going to start this proof using the fact that the transpose of I is equal to I. And we also have to remember that if we have a matrix, for example n, and we multiply n by the inverse of n, the result will be I. So using these two equations, we can rewrite the left hand side and the right hand side of the equation. And so, for example, on the left hand side we can write it as m to the minus 1 multiplied by m. Remember, this will just be equal to I, and then the transpose of this will be equal to mt multiplied by mt to the minus 1. If we then, using previous identities, rearrange the left hand side of the equation, we will get that mt multiplied by m minus 1 t is equal to mt multiplied by mt to the minus 1. And if we then multiply both sides of the equation by mt to the minus 1, so the inverse of mt, the transposes of m, each side of the equation will cancel out, and we will be left with m to the minus 1 transposed is equal to the transpose of M and then the inverse taken.